What's up, guys? It's Ocean. I have some old Call of Duty gameplay in the background. I recorded this like 2 years ago. I can't even tell you what Call of Duty game this is, to be honest. I'll probably figure it out later. But regardless, I'm here to talk to you guys about my programming language, Hum. It's currently in pre-alpha. The basic question behind Hum is pretty simple. Why is so much of what an experienced programmer knows still implicit? If you give a senior systems engineer a random function, they don't just read the code line by line. They're asking questions like, what does this function change? What does it allocate? What does it own? What can it borrow? What can fail? What assumptions does it make? What side effects does it have? What security boundary does it cross? What does it guarantee when it returns? And maybe even, what is the computational cost? The weird thing is, in most programming languages, these answers are just scattered everywhere. Some of it is in the type system, some of it is in the comments, some of it's in the documentation, some of it is hidden in implementation details, and a lot of it is just tribal knowledge that experienced developers have accumulated over 10 or 20 years. And I'm sorry, but I think we can do better than that. The direction I'm exploring with Hum is what I call an intent-first systems language. Instead of treating the implementation as the primary source of truth and then attaching comments around it, the function can explicitly describe its contract. What does it need? What does it ensure? What state can it change? What resource does it use? What does it protect? What does it trust? What are known failure cases? And finally, what does it actually do? That distinction is important. The contract is the promise. The implementation is how you fulfill that promise. And then there's the third layer that I think becomes increasingly important: evidence. A programmer can say, for example, that an operation should be O of n. That doesn't automatically mean the compiler has mathematically proven it. So Hum tries to keep a very strict distinction between things that are declared, things that are statically checked, and things that are actually proven or backed by evidence. I think that becomes especially important as AI agents write more software. And because AI agents generate 10,000 lines of code super fast, the hard part isn't producing code anymore. The hard part is determining what the code is allowed to do. What is it supposed to do? And whether it actually satisfies those constraints. So instead of giving an agent a giant code base and saying, figure it out, imagine giving it a structured semantic surface. Here are the invariants. Here are the ownership rules. Here are the allowed effects. Here are the trust boundaries. Here are the guarantees. Now modify the implementation without violating them. That's a much more interesting model of agentic software engineering. And there's another part of language design that I've started appreciating a lot more. A programming language isn't just syntax. People tend to look at a language and immediately focus on whether it uses braces, indentation, semicolons, whatever. That's probably the least interesting part. You have syntax, which is how programs are written. You have semantics, which define what those programs actually mean. You have a type system, which defines which programs are considered valid and what properties can be established statically. Then, in a systems language, you start dealing with ownership, effects, memory safety, resource behavior, concurrency, and all the other constraints. Once you understand those layers, you can almost reverse engineer why languages evolve the way they did. Take C++, for example. A lot of its complexity makes sense when you remember that it has decades of history, enormous amounts of existing software, and very strong backwards compatibility requirements. Rust comes along much later and gets to make different choices. Rust basically says, these are entire categories of memory behavior that we're going to make explicit and statically reason about. Ownership becomes part of the programming model. And I think the next generation of languages can go another step. Not just making memory ownership explicit, making engineering intent explicit. One philosophy I keep coming back to is that you shouldn't need 40 years of experience to know what questions you're supposed to ask about a function. I'm sorry, I know I'm completely unhinged right now. I'm crashing out, but I'm serious. The language itself can teach you those questions. If every operation has clearly labeled places for preconditions, guarantees, effects, ownership, and failure behavior, a beginner starts learning to think like a systems engineer simply by reading the source. That doesn't eliminate complexity. Systems programming is inherently complicated. What it does is organize complexity. And I think that distinction matters. Hitting complexity is dangerous. Labeled complexity can actually make a system easier to reason about. Hum is still extremely early. It's a prototype, and a lot of these ideas need to survive contact with real programs before I'd make any grand claims about them. But that's also what makes programming language design interesting. You're not just designing syntax, you're designing a way for humans and machines to reason about computation. And now that AI agents can participate directly in compiler development, research, testing, and implementation, I think this is probably one of the most interesting times ever to experience with programming languages. We have decades of mistakes to learn from, decades of language research, decades of open source engineering experience, and now we have systems capable of helping us explore the design space dramatically faster. So that's basically what I'm doing with Hum, trying to take the things experienced engineers normally carry around in their heads and make it part of the language.